right. So this is kind of where we left off last time, um, trying to obtain some sort of expression for the radial shear stress distribution in a circular cross section, or you might think of this as like a shaft, a screw, or whatever. So we had gone up to here, which is an expression for the strain, for the shear strain as a function of radius. And I'm going to shoot myself in the foot in just about 20 seconds because I forgot to make it so that I could actually write notes. 1 second. I knew I was forgetting something. Not a terrible amount of use having a board if you can't write on it. Okay, let's try this again. Okay, so we had gotten up to here, which is cool. Gives us a radial strain distribution, and you might think that we can parlay that into a stress distribution by multiplying everything by the modulus of rigidity, because because of Hooke's law, stress is related to strain by how stiff material is. So if we do that, and note this is the same thing as gamma. For some reason, it comes out as like a Y thing in Word. Anyhow, so I get like G gamma equals rho over C gamma max, where rho, as you remember from before, is any radial distance inside of the shaft. And C is the radius of the shaft. So I can draw a line to any point rho, I can draw any radius that is rho long, and it'll be inside of the shaft, and then the actual outer thing, it's called the actual outer radius of the shaft itself is C. Just make sure we have terminology straight. So if I do that, I multiply by modulus of rigidity. He'd say, hey, that's like a shear stress, right? So I can rewrite this as tau equals rho over C. And then if I group the modulus of rigidity and the maximum shear strain on this side, I could say if that's my maximum strain, it's also going to be my maximum stress, my maximum shear stress. So I can grab this and say, hey, look. Now I can say that for any radius, my local shear stress is going to vary linearly in proportion to my maximum shear stress. So at the center of the shaft, where rho e equals 0, I have no shear stress, and as I go out towards the surface, I'll gradually build up to the maximum value of shear stress. So that gives us our distribution. We have so kind of the sum of last lecture was we can figure out how, for at least small angles and elastic materials, how the shaft is going to strain or how it's going to twist is just when you apply torque to it. And based on that, we can come up with an idea of what the stress distribution is. Okay? You all on board with this? Sweet. All right. So let's see if we can start doing crap with this. Okay. So, based on this, get out of my way, a little recorder icon. Okay. So based on that, if we have tau equals rho over c tau max, we can go back to this is the equation that we started out with way back beginning of last class. Just looking at a circular cross section with a torque on it. And that torque, if I replace, if I look at that internally, really it's like a whole bunch of little elemental areas with forces acting on them at some distance rho from the center in each of these elements. They're differential elements with area dA. So I can kind of parlay that into a expression of a shear stress acting on that element. And if I add up all those elemental shear stresses acting at a distance from the center, I can call that kind of expresses the torque that's acting on this element. All right. So really what we're going after here is we kind of have a relationship between torque and shear stress, but it's not really that well defined because this is a local shear stress. It's hard to integrate that. And what the crap's this dA business going on? If we could make a lot of this simplify, or if we could recast it, we could use this equation for something like design, right? If I wanted to make a shaft for some mechanism, be it if I'm trying to draw water up from a well or design a drop shaft for a vehicle or whatever, and I know what torque I'm going to have to apply to the shaft, it'd be awfully nice if I could figure out what the anticipated shear stress would be based on that torque. So if we could find some relationship here, that'd be awesome. So let's do it. So if we start out, we have this expression here, and we know that we can get tau max. That'd be pretty straightforward. It's one number. It's not going to change, right? Because it's just the shear stress that's on the surface of the rotating of the circular part. So if we could recast this in terms of tau max, maybe we could start getting something. So if we substitute this in, so integral rho over c tau max dA equals torque, then group some like terms. I know that my radius and tau max are constants, right? So I can take them out through the integral sign. So I get something like tau max over c integral rho squared dA equals t. Now this still leaves us with all this garbage here, right? But have you guys ever seen something like that before? Maybe not r squared dA, but maybe like r squared dm. Have you guys ever seen something like that before? Does that look familiar? Like a moment of inertia kind of thing? Okay. Well, if you wanted to integrate a moment of inertia, this would be like if you had a moving, if you had an object that's like moving in circles or rotating, you can find its moment of inertia, or how much it resists changes in angular motion. In the same way, I wanted to bring a piece of cardboard for this work. In the same way, in materials, we often talk about area moments of inertia, and this is an expression of an area moment of inertia, which is a similar idea, but it has nothing to do with mass. And the idea here is that, say that I have this folder here. If I'm bending it like this, it bends really easily. If I bend it like this, I can't bend it unless I'm going to start ripping the thing, right? And the difference, because I can still get a pretty good, I can still get a pretty good grip on the folder. The difference isn't based on how I'm holding the thing or how I can apply the loads. The difference is that if I hold this folder horizontally, there's less of an area moment of inertia to resist the bending loads. It's kind of like if you think of what's going to stop this folder from flexing, or stop this folder from flexing. If there was more stuff, if there was just more stuff going in the direction that I'm trying to bend it, it'd be easier for it to resist. It's kind of like if you had a if you're trying to bend a really thick book versus a really thin book. You guys following what I'm saying at all? If not, just say so, please, and I'll try to reformulate. The idea is that there's more stuff to resist the load, and the more that it's distributed, the better it can do that. So in the case of this folder, if it's oriented horizontally, it has the same amount of area as if it was oriented vertically, right? However, when it's vertical, the areas is all distributed in such way that it can resist the bending better, as opposed to if it's horizontal, where it's all kind of along the same line that the folder is bending around. So you might think of it if you're trying to stop something from bending, if you're trying to if you have a plank and you're trying to hold up a bunch of weight, it's easier to bend down and pull the plank up than try to lay down and pull up a little bit at the end. And it relates to the same sort of an idea. You're adding stiffness in different locations. So to kind of sum all of that up, the area moment of inertia is a measure of how much stiffness is effectively added by what the object's shape is. So there are various formulas for this in the back of the Mechanics of Materials book. Or online, they're really straightforward to just look up, and they're for different things. So like this is this specific area moment of inertia is something called the polar moment of inertia. So come on, you can do this. There we go. The polar moment of inertia. So if I had a brick and I bent it like that, say that I'll draw some coordinates on this. Let's see. No, that's not the X. Call this Y, call this X, call this C. Okay. So if I'm trying to exert a moment around the x-axis, say, the area moment of inertia that would resist that most is IXX or IX, the area moment of inertia around the x-axis. If I was doing the same thing around the y-axis, what's called that guy here would take care of it. However, if I'm going around the Z, you might think that it should be some combination of the two, right? Because instead of just bending around one axis or the other, I'm kind of moving through that entire plane. So you can express the polar moment of inertia. You can think of the polar moment of inertia as something where you're trying to resist a torsion of an area. And in this case, where I'm rotating around the Z, you can find in that polar moment, so I can kind of denote it like that. You can find that polar moment of inertia by adding together the area moment of inertias around the other two axes. These are the two that are in the plane of rotation. For reference, these area moments of inertia are in units of what's called length to the fourth power. So you might have, if you think like integral r squared dA, it's called a differential area. So that is units of like length squared, and then this is a radius, which is units of length, and then it's squared. So area moment of inertia, polar moment of inertia, units of length to the fourth power. And you can get them from each other. Now the trick is they have to be about the correct axis. So here, this is called I have the polar moment of inertia around the z-axis or around the axis of rotation. And if I'm trying to spin this whole thing around z, if I want to find that polar moment of inertia, if I don't have it for some reason, and I want to find it from two other area moments of inertia that I do know, say the area moment of inertia around the x and the y-axis, I just have to make sure that the point where the y and x-axis intersect is indeed where I have the z-axis coming through, because I can have multiple bodies. Say I have a second brick here, and I'm spinning this whole thing. I can find the polar moment of inertia here, polar moment of inertia here, and there's a way that I can combine them in order to make it all work. Don't worry about that too much yet. Just know that you have to be consistent in your axes, and it's called, if you're trying to find a polar moment of inertia from two area moments of inertia, you have to make sure that you're sitting on the same axis. If I said something like parallel axis theorem, would that mean anything to you? No? Okay, cool. Well, we can talk about that later on, and then for now, let's just look at. I have to bring my book today. Ian, do you have the book with you? Okay, cool. I forgot to bring it today. Of course, it has a formula that I want. Let's look it up quick. So what I wanted to do is talk about, there we go. Okay. Moment of a circle, pi r to the fourth over 4. Okay. Cool. So something that you can do with polar moments what's called moments of inertia in general is, if they are around the same axis, you can start to add and subtract them. Like you might think, if I have a solid circle, if I have a solid shaft here with radius r, that's going to have some inertia if I try to turn it, right? If I try to spin it. If I have that same shaft, but I hollow it out a little bit, so I have some inner radius, terrible. Yeah, that'll work. R1 in some outer radius. That's going to be easier to spin, right? It's going to have less inertia, less area. It also have less lower area moment of inertia, right? The question is, how in the world do I find that, right? Hey, and that's going to come through manipulating these, a combination of these area moments of inertia. Now, for a circle, you might think that it'd be, what you call it, it doesn't matter which way you bend a circle, right? It's not, the shape's not any different in any given direction. It's going to be as hard to bend in one direction as it is in the other. Unlike this folder, which is really easy to bend one way and really hard to bend in the other because the shape is different. Here, the shape is the same. So you might think that IXX is the same as IYY, and for a circle, that's pi r to the fourth over 4. So if I wanted to find, say, where r is just whatever the radius of the circle is. So don't get tied down with stuff here. Don't get tied down with me saying that it is only r. It's not r naught or r1 or whatever. Okay, so if I wanted to find the polar moment of inertia from this, I just add these two. I just add this to itself twice. So IXX plus IYY, right there, here, Ian, and get something like pi r to the fourth over 2, right? Cool. Yes?
So this is for a shaft?
It's for any circular object. Shafts just happen to always be that.
So if you rotated it around like just a regular ring, so like around an axis that went through both ends of the circle rather than through the middle of the circle?
So if I rotated like this,
yeah,
would that be the same moment of inertia as what?
As like you put it through the center and rotate it
around? No, it would not. It would not be. If I'm rotating like this, then this is like my x-axis. I'm rotating around my x-axis. That's my area moment of inertia. If I'm rotating around my y-axis, that's my area moment of inertia.
But that would be the same as the next one, probably.
Yes, in this case. If I'm spinning like this around its long axis, then it's some combination of these two in what's called a polar moment of inertia. Yeah. Does that answer your question?
Yep.
Great. Okay. But this answer doesn't correspond to a ring. It corresponds to a circle right now. But we can get a ring out of this because moments of inertia can be additive. So if I know the moment of inertia for a circle, which is called for a solid circle, and a ring is just essentially me hollowing out that circle a little bit, then I can say, well, J solid is pi r to the fourth over 2. And if I'm just hollowing out a bit of that circle, I can just say, well, I'm just going to take my solid polar moment of inertia and just subtract out what I removed. So in this case, be like J solid minus J inner, or something like pi r to the fourth over 2. Or sorry, r naught is what I used for the outer radius, minus pi r inner radius to the fourth. O over 2 would get me the polar moment of inertia of the ring. Does that make sense? Cool. I like it. All right. So that's moments of inertia in a nut in a nutshell. And if we apply this then to the last slide, so this guy we sledgehammered it down until we had something like tau max over c, so the radius of shaft, integral rho squared dA equals t. If we say, hey, look, that's really just a polar moment of inertia, because this is a shaft that we're turning around its long axis, if we can find that algebraically for a number of different shapes, we have an expression relating shear stress and torque. Yes, Grace. Because it's called because notation is weird. I'm sorry. It's because it's what the book was using. So I was trying to stay consistent with the book in case anyone was looking along with it. But you could easily do that if you wanted to. So yeah, that's so what's called. We can come up with expressions. Yeah, make sure I'm saying the right thing. Yep. So we can come up with expressions like this to relate torque and shear stress together, which is cool. Gets us one step closer to a design in application. All right. Are you going through that? Okay. So before we get too much further, speaking of design things, we're going to have a superposition redux. So the same way that I could say take a shaft, or not a shaft, a bunch of blocks stuck together, and I have different forces acting on it. And I can take sections of this and find the forces acting on that section kind of marching across it. I can do the same thing with torques. So let's just kind of walk through that quick. So, say that I have the shaft here, has a 6 kilonewton meter torque being applied to this end, say through a gear or something like that, or a friction roller or whatever. There is more shaft here, but it doesn't actually matter. I can take a section wherever I want, and some moments and some forces. Here we're saying that there aren't any forces acting on the shaft. There are only torques. Try and make life a little bit more straightforward. So in that case, what has to be the magnitude of torque AB? Okay, yeah. So in order to satisfy Newton's third law, assuming that this shaft is not accelerating in any way, shape, or form, TAB must be the same as TA. And most of our analysis is for steady state systems, right? Because that's normally where things operate at a steady state. I mean, your car tries to operates best at a steady state. If you're not varying speeds or anything like that. So that's usually a good basis for design. So in this case, torque balance TA must equal TB. If we move further up the shaft, we get a second friction roller, going like this. What does torque BC need to be in order for Newton's third law to be satisfied. Yes. Right. Because if I say like this is my this that's my positive direction, TA plus TB minus TBC equals 0. Just do the methods there, and you can see that TBC is equal to TA plus TB. It's same as when we had a bunch of forces stacked up on, say, a rod or a brick or whatever, and you had to sum them up going across it. And this, and kind of like in the homework that you handed in today, or before, what you call, I think last week's homework problem, where you had, it was like a test coupon like this, and there was a force pulling at each end. And the question is, how much is it going to stretch, right? So you figured out the strain for this section, strain for this section, strain for this section, found the respective deformations, added them all up. You didn't find deformation for the whole thing. You found it for each section and added them together. That's the principle of superposition at work. You can kind of treat, even though it's one block of material, either with the forces or with the torques, you can kind of chop it up, treat it as a bunch of independent problems, and solve them all individually, and then combine them all, and the answer still pertains to the whole system. So that's the beauty of superposition, and it still applies to things that rotate. Okay, cool. That makes sense. Cool. All right. All right. Oh, hey, actually already did this slide. So, oh yeah, that's what I want to do here. Okay. So we said before, we have solid shaft, radius r, say, and we have some linear shear stress distribution on that, which I'm writing as like some that looks like a force. It's just trying to illustrate the magnitude of it in another way. What if that was a hollow shaft? Because you might want to do that. Let's try to get this right first. What you might want to do if, say, weight's a concern. Say that you want to have multiple shafts inside of each other. I'm a helicopter nerd, so that's like how they make some of the more modern helicopters. They have shafts inside of those shafts, so you can have two things spinning around the same axis, stuff like that. It's lighter or whatever. You might want to do it. What would our stress distribution look like? Because it's still going to be linear, because that's what you call it. Because if you do an analysis for a circular section, that's how it comes out. But where would the 0 for the shear stress distribution be? Would it still be at the center? Would it start here? What do you think? Why? Okay. So let's think about it like this. All of this material is some radius from the center of rotation. Would any of it have zero stress? If it's all some distance from the center. It would have zero stress?
No. All stress.
Why?
Away from the center.
Yeah, because it's away from the center. If it's away from the center, it means that the material can resist a torque because it has some stiffness, right? The material has some stiffness, and it's some distance away from the axis of rotation, so it can resist a torque that's being placed upon it. If it was at the center, its moment arm would be zero, so it couldn't resist a torque, and that's why in a solid case, shear stress is zero there. So here we know that all the material in this ring has to resist has to resist whatever torque's being placed upon it. It's just evident from the geometry. So in order to do that, it actually follows the same shear stress distribution, still a linear thing. The only difference is that the bit of the distribution inside of the center of the ring, and it only exists theoretically, and what stresses are contained in the ring are intensified a bit because there's simply less area to carry the torques. Makes sense. It's the same thing as in bars and beams resisting forces. You have a certain amount. You have a certain amount of area. You can resist just more stress. You have a certain amount of area. You can resist more torque. Here we simply have less. So it's the same. So it's the same. So it's the same analysis, but if you look at what was it? Torque equals tau max J over radius for this guy. If we look at something like this, is again we're going to have a different polar moment of inertia to term, but everything else is essentially the same. All right. So one last thing for today. I think it's all concepts if I'm remembering correctly, so no math. So we got torques, we got stresses, and we got to look at how things fail. So these should look somewhat similar, right? From when we were pulling things apart or pressing them apart, when you're getting these either flat surfaces or these what you call these angled breaks. Except in torsion, it's a little bit different. Actually, there is going to be a little bit of math today. Okay, so like this guy here, you can see that it's been torqued. What's called the splines on the end of this shaft, which are what connect shaft into some sort of a receiver when you have a rotating part. That what's called a hole, they're bent. So there's obviously been some deformations. There's been some stress, and it's a pretty much flat break. As opposed to this guy here, where it's like this 45-degree helix kind of thing. Now, if we think back to what is called, we think back to ductile and brittle failure from bars just being pulled in tension or compression, and we might be able to start to draw some hypotheses here, like there might be a difference in one of these being brittle or ductile. You might guess that this would be what, more brittle, right? But in torsion, it's a little bit different. Remember when we were pulling in tension or whatever, because of the orientation of a stress cube and how that changed, whether or not that cube was experiencing mostly shear forces or normal forces that caused the particular angle of the break. like if we rotated that shear cube 45 degrees for something that's purely in tension, it became a pure shear problem, which called that stress cube only saw shear stress, and that's how ductile things broke. And that's why, like for that rock that I brought in the other day, the top where it broke was shaped like a V. In torsion, it's a little bit different. Here's some stuff that you can look around at if you want. This is from the Jeep that I had like a decade ago. This was my oil pan plug. It broke when they tried to pull it out once. And you can see that that's a flat break. This is what's called a bolt. I forget where I was trying to tighten it. It failed in a similar way. And both of those, even though the brakes are flat like this, both of those are ductile materials. They're steel. They're not brittle. So in torsion, things actually act reverse. They fail in a reverse fashion of when they fail in tension or compression, physically speaking. And you can kind of get that out of little shear cube analysis. So we have this guy here, which called that guy being a stress cube, that's oriented parallel to the axes of the material, and it's in pure shear from torsional stress. If I take that and I start to rotate it, just like when I was pulling things in tension or compression, you might think that now there's some combination of shear and normal stresses, right? So if I have, say, how do I say this? Some stress is force over her area. If this starts out as, I'm going to say this, if I have my shear, if I have my shear stress times his area, say like the cross-sectional area there, call it A naught. That's one way of writing a force, right? This would be like a differential. You can say this even be like a differential area if you wanted to, what's called generalize it. This would be over some initial whole area here. If I start rotating, I have to take into account some change in those areas and some change in those areas and forces according to the angle of rotation. And this is all the same essentially from when you did it on homework 1 and you were rotating planes and forces is around, right? Yep. Areas at the bottom different. They are not. Eventually, yeah. So it's called as Anna said, these are going to go away eventually. Cosine and sine, if theta is 45 degrees, kind of the same way that if I had pure tension and rotated a stress cube 45 degrees, it became pure shear. If I make theta 45 degrees, we're going to see these two terms go away because what's called cosine and sine of 45 degrees is the same thing. I'm going to see that my stress cube is now in pure tension or compression, however you want to say it, which is at the same magnitude as the shear stress. So if I fail in, if I'm a brittle material and I fail usually in normal stress as opposed to ductile materials which fail primarily in shear stress, I'm going to fail along a 45-degree plane. If I'm a ductile material and I fail primarily in shear stress, I'm going to fail along a 0-degree plane, one that's what's called perpendicular to the long axis, the same as in those bolts that I passed around. Does this sound good? Sort of, kind of.
Yeah.
All right. Well, we're stopping there for today. If you have any questions, I'd be happy to entertain them.